So hello everyone. In the class we have discussed about floating point number representation in general, and in this video I will discuss about floating point number representation as per IEEE 754 standard. Okay, so the core part of this IEEE standard is about the normalized representation of values. So what do we understand by normalized representation of values? Let's understand this. So suppose let's take an example of a decimal number. Suppose I have this number 1 2 3 4 5 6 into 10 raised to power minus 1. So I can represent this number as 1 2 3 4 5.6, and this will be 10 raised to power 0, or I can write it like this: 0.56 into 10 raised to power 1, 123.456 into 10 raised to power 2, or 12.3456 into 10 raised to power 3, 1.2346 into 10 raised to power 4. Now when we have this single digit before this decimal, this is called as normalized representation. Now in this normalized representation, it's a decimal number, but in this normalized representation, this part is called as exponent, and this part, the fractional part, is called as significant or mantissa. This is a decimal number where we have total 10 digits from 0 to 9 and the combination of these 10 digits can represent any number. When we talk about binary number, we have just 2 digits, 0 and 1, and the combination of these 2 digits can represent any number. And if we talk about binary representation, normalized representation of a binary number, here instead of base 10 we will have base 2, and the first bit before decimal will always be 1. We don't write it, it is explicitly known that this bit will be 1. Okay. Now this IEEE 754 standard has two formats for binary floating point representation. So the data type float uses this IEEE 32-bit single precision format, and data type double represents data type double uses this 64-bit double precision format. Okay, here the most significant bit, okay, this one or this one, the most significant bit indicates the sign of number. So 1 is for negative number and 0 is for positive number. The next 8 bits or 11 in case of 64-bit representation, these 8 bits store the value of the signed exponent of 2. That is, it represents this thing, 2 raised to power 6 or whatever. And the next 23 bits, the remaining 23 bits are for significant or mantissa. Okay. Now let's see how this floating point numbers are represented in single precision normalized format. So for simplicity, we will discuss only the 32-bit floating point values. Okay. So the formula representation for representing the value of a normalized number is -1 s into 1 m 2 e raised to power minus 127. Now let's take each and everything one by one. So this s, okay, this is a sign bit. S is 1 for negative number and it's 0 for positive number. So accordingly we will have sign. If it is 0, the value will be 1. If it is 1, that means it's a negative number. Okay. Now this normalized significant, this is a normal representation, normalized representation. So the normalized significant is 1 and this is binary dot m. So here this binary dot, the binary point is before bit 22. And we don't explicitly write this, 1 is not explicitly present. We will see example like how this 1 is represented here and how it is used. Okay. So this is the normalized representation, but this is by default it is present. So we don't explicitly write it. So we have all 23 bits for representation of mantissa part, significant part. Okay. Now the actual exponent is biased by 127. So to get the value of e, the actual value of exponent is subtracted by 127. This is just to enable only the positive values here, exponent part. So this is the formula representation. It is used as it is. This is the format for representing floating point values in a normalized representation. Okay. So let's understand this thing with example. So all these things and all this formula will become more clear to you. So let me take a 32-bit pattern, 32-bit binary number, which is this 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. So this is the binary number which I have taken for representation. Now let's find out what is its decimal equivalent. Okay. So the value is, according to this formula, it is -1s into 1.m 2 raised to power e minus 127. So this is the formula we have. Okay. Here the sign bit is 1. So it is a negative number. I will write it like this. And what is the mantissa part? The 8 digits. The 8 bits are representing exponent and remaining 23 bits mantissa. So in this particular example, let's first take what is the representation for exponent part. So I am first taking the exponent part. Okay. So exponent part is the 8 bits, this and this. So I have 101101110. What is the decimal value of this? 1, 2, 4, 8, 16, 32, 64, 128. So I'll add 128, 32, 16, 4 and 2, which is equal to 182. So the exponent part is this is 182. So 182 minus 127. Okay. And this is my Mantissa part. Mantissa is represented like this. So I will write it like 1 point and this is my Mantissa 0, 1, 1. Okay. This is the normalized representation according to this formula. Mantissa I will write as it is and 1 is explicit. So 1.011. So zeros after decimal has no significance as such. So I am writing just this one, which is equivalent to minus 1. So this is minus 1 into 2 raised to power 55, and convert this into decimal. So 0.011 it will be 2 raised to power minus 1 into 0 plus 2 raised to power minus 2 into 1 plus 2 raised to power minus 3 into 1, which is 1 plus 0 plus 1 by 4 plus 1 by 8, which is this part is 1.375, or I can write it minus 1.375 into 2 raised to power 55. You can solve this, or this can be considered as your final answer. Okay. So using this normalized representation and IEEE 754 standard, this is how we will be representing. This is how we represent binary numbers and how these numbers are converted into decimal. Now let's take an example in which we convert a decimal number into binary. So let's take this example, which is 105.625. So first convert this 105 into binary. We will use radix division method, in which we will divide this number by 2. This is remainder. Again I will take 52, divide this by 2, 26. Then 13, 2, 6, 1 remainder. So this is my binary number for binary equivalent of 105. Now To convert this fractional part, I will use radix multiplication. So I will take this decimal part, multiply it by 2. This is the output. I'll take the integer part out and again multiply the fractional part by 2. So I get 0.500. Again I will take the decimal part out, that is, integer part out, that is 0, and the decimal part again multiply it by 2. Now I don't get any fractional part, so I stop here and just take out the integer part. So the decimal equivalent or binary equivalent of this number is, I am writing it here, it is 111101 1001 decimal 101. Okay. Now I will write this number in a normalized form, in which the first digit should be 1 and all other digits will be, means I will shift this decimal here. Okay, so this is my normalized form. So how many places I have to shift? 1 2 3 4 5 6. So I can write it like this: 1.101001 and 101 into 2 raised to power, this is my base, 2 raised to power 6. Okay. So can I write it like this? Okay. Now this I have written according to this formula. Now write the binary equivalent of 133 and binary equivalent of 127. So this is 00101 minus 0. Okay. Now this is my exponent part and this is my mantissa part, and since it's a positive number, my sign bit is 0. So I write this number as 0 sign bit, then 8 bits for my exponent. So I write 1 0 0 0 0 1 0 1, and remaining bit, this is my mantissa part, 1 0 1 0 0 1 1, then remaining bits are 0. Okay, so this is my binary, the floating point representation in single precision IEEE 754 standard. Okay, now let's take an example in which this fractional part gets repeated again and again. So let's take an example. Let's convert this 263.3 in binary in IEEE 754 32-bit floating point representation. So I have done it already. First I will convert this 263 into binary, and which is equal to 100,000,111. Sorry, this is 2. And this 0.3 decimal is 0, 1, 0, 0, 11, 0011, 0011, and this pattern repeats. Okay. Now how to represent this number? So this number 263.3 is actually 100,000,111 dot 010011001100 and so on. I will write this number in a normalized form. This is my first step. So first write this number in a normalized fashion. So I have to move this decimal here. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll write 1.00. Zero, zero, 1, 1, 0, 0, so on, into 2 raised to power 8. Since I have shifted it 8 points ahead, 8 places ahead. Okay. Now write this according to this formula, which is 1.00001110011001100, so on, into 2 raised to power 135 minus 127. Okay. Now 135, binary equivalent of 135 is 1, 0, 0, 0, 0, 1, 1, 1. Okay. So this is my binary equivalent of 135. This is my exponent part. It's a positive number, so sign bit is 0. Then I will write this exponent part. Okay. 0, 0, 1, 1, and this Mentisa part thereafter. So I'll write it like this. So I have taken 3 zeros, then 0, 0, 1, 1, 1, 0, 1, 0. Zero, 1, 1, 0, 0, 1, 1, 0, and 0, 1, 1. So we will just complete. We can write this Mentisa part using 23 bits. So this is my final number. So there are some more details regarding 64-bit double precision representation, but for this course this would be sufficient, and this is in the scope of your C computer programming subject. Okay.